comet, asteroid, or something else? A Harvard astrophysicist believes there's a strong likelihood this is a craft of alien origin.
First, its brightness implies that if it represents reflection of sunlight from a solid object, it needs to be 20 kilometers in diameter. That's bigger than Manhattan Island. And this is a giant rock.
The arrival of a massive interstellar object shooting toward the inner solar system has drawn the collective attention of astronomers, physicists, and curious minds worldwide. What makes this discovery so extraordinary is not merely its vast size or the blistering speed at which it travels, but its peculiar trajectory that intersects with the path of another interstellar traveler, 3I/Atlas. The designation 3I places Atlas among the very few confirmed interstellar objects ever observed, following Nin, Oumuamua, and 2I/Borisov. Now, with this new cosmic visitor racing toward the same space where 3I/Atlas drifts, questions about interstellar dynamics, cosmic coincidences, and the mechanisms that fling such objects into our solar neighborhood come to the forefront. Before we start, smash the like and subscribe buttons for more updates. The enormity of this object is its first defining characteristic. Observations suggest that it is significantly larger than the handful of interstellar wanderers previously catalogued. Unlike Oumuamua, which was elongated and only a few hundred meters long, or Borisov, which resembled a comet but measured just a few kilometers across, this new body spans tens if not hundreds of kilometers in diameter. To put it in perspective, it rivals or surpasses some of the largest asteroids in the asteroid belt. Yet it does not belong to our solar system at all. The physics of accelerating such a bulk across interstellar distances implies a violent and cataclysmic ejection process from its native system. Perhaps it was expelled by the gravitational kick of a giant planet, or torn from an unstable orbit when its parent star underwent significant changes. Whatever the origin, the sheer kinetic energy bound within its mass and speed paints a picture of unimaginable power. Speed itself is the second astonishing factor. Typical comets or asteroids that orbit within the solar system travel at tens of kilometers per second, their motions bound by the gravitational tether of the sun. This interstellar body, however, streaks along at extreme velocity, easily surpassing 100 kilometers per second relative to the solar system. Such a speed confirms its alien origin. Only objects unbound to the sun can exhibit these kinds of hyperbolic trajectories. Yet in this case, its vector is not random. Its course appears aligned in such a way that it crosses paths with 3I/Atlas, another visitor already recognized as an outsider to our star's dominion. This eerie targeting raises both scientific wonder and speculative unease. Interstellar space is vast. The odds of two objects from different stellar neighborhoods converging so tightly within our field of view are almost incalculably small. The situation hints at dynamics we may only just be beginning to understand. The scientific implications are staggering. Two interstellar objects meeting or passing near each other inside our solar system is an unprecedented observational opportunity. It would allow astronomers to study not only their compositions and structures, but also their relative interactions under the influence of the sun's gravity. Instruments could capture high-resolution data on surface reflectivity, volatile outgassing, and spectral fingerprints that might betray elements or compounds uncommon in our solar system. These chemical signatures might carry the history of distant star-forming regions or the remnants of exotic planetary processes. With careful tracking, scientists might even detect how their trajectories bend relative to each other, offering a glimpse of mutual gravitational nudges. It would be a cosmic laboratory staged on our doorstep, a chance to compare the DNA of different stellar nurseries by studying chunks of matter hurled across the galactic medium. At the same time, the cultural and philosophical implications cannot be ignored. Humanity has long speculated about messengers from the stars, about omens arriving on cosmic winds. To see two such objects align within such proximity invites narratives that stretch from science to mythology. Ancient traditions often imbued comets and celestial wanderers with significance, reading in them signs of change, upheaval, or revelation. While today we understand them as natural objects obeying the laws of physics, the psychological effect of their arrival retains echoes of awe and apprehension. A massive interstellar body appearing to chase or intersect another cannot help but spark imaginations. Some may see patterns, intentions, or cosmic choreography, while others stress the impartial chaos of celestial mechanics. Both responses reflect the human need to make sense of extraordinary phenomena. The practical side of astronomy, however, focuses on data. Tracking such a fast-moving interstellar traveler requires a global effort, harnessing observatories from Earth's surface and telescopes in orbit. Radar, spectroscopy, and thermal imaging will be marshaled to extract every possible clue. Because it is both huge and fast, the object poses observational challenges. Its brightness fluctuates, its shape may be irregular, and its speed means windows of clarity are fleeting. Moreover, if it passes close enough, its gravitational pull could perturb not only 3I/Atlas, but also nearby smaller bodies, slightly adjusting the architecture of local orbits. Measuring these subtleties demands precision, but the reward would be invaluable. A chance to see gravitational interactions play out between two alien objects within our sightline. There is also the broader implication for galactic astronomy. Every interstellar visitor carries with it the history of its birth environment. Dust grains embedded in its structure may have formed in the outskirts of a nebula or during the cooling of a protoplanetary disk around a young star. Isotopic ratios, such as deuterium to hydrogen, or the abundance of noble gases trapped within, act as fingerprints of stellar chemistry. If 3I/Atlas and the new massive object originate from entirely different systems, comparing their properties would give us two independent samples of material from outside the solar system. That alone would revolutionize our understanding of the diversity of planetary systems. Up until now, our direct knowledge of exoplanetary matter has been limited. Here, interstellar visitors deliver samples themselves, albeit at scales far too large to capture fully. Still, telescopic spectroscopy might act as a surrogate, revealing the clues we cannot physically collect. The trajectory, targeting 3I/Atlas, carries another layer of intrigue. Astronomers are trained to resist the temptation of coincidence. Yet this convergence challenges probability. One hypothesis might be that both objects were expelled from the same star system at different times, now coincidentally meeting again after millennia adrift. Another possibility is that galactic dynamics funnel interstellar debris along preferential routes, similar to currents in an ocean. If true, then interstellar highways exist, channels carved by the gravitational interplay of stars and molecular clouds through which objects more frequently drift. In this case, 3I/Atlas may not be uniquely targeted, but rather both objects happen to ride the same galactic stream. Studying this potential would open a new frontier in astrophysics, where we move beyond individual star systems and begin mapping the traffic lanes of the galaxy itself. The psychological impact on humanity should not be underestimated. People across the world are drawn to stories of cosmic arrivals. The announcement of Oumuamua electrified the imagination because it was the first tangible sign of something unquestionably foreign. With each new interstellar visitor, the realization deepens. The galaxy is not a static place, but one where debris and remnants constantly wander between stars. Now, with an enormous body streaking toward an intersection with 3I/Atlas, the drama heightens. Media coverage, artistic interpretations, and speculative theories will flourish. Conversations about the fragility of Earth and the grand scale of the cosmos will resurface, reminding humanity of its smallness, yet also its remarkable ability to observe and comprehend. On a technical level, planetary defense networks will also pay attention. While the object is not on a collision course with Earth, its size demands scrutiny. Objects of this magnitude carry destructive potential far beyond the imagination if ever they did intersect with our planet. Monitoring its distance and path ensures that even a slight uncertainty does not turn into a threat. More importantly, this highlights the role of vigilant sky surveys in protecting Earth. Every interstellar intruder, whether harmless or hazardous, reinforces the necessity of watching the skies with unblinking attention. The new arrival thus strengthens the infrastructure of observation and preparedness, sharpening tools that one day could be critical in averting catastrophe. The timing of such an event could not be more pivotal for the sciences of space exploration. Missions are being designed to chase comets and asteroids, to capture samples, and to probe planetary origins. Imagine if one day technology advances enough to intercept interstellar visitors directly. A spacecraft could rendezvous, map, and sample such a body, bringing back fragments that formed light years away. This current massive visitor, though too swift and massive for our present capabilities, will fuel the dreams of engineers and planners. It underscores the need for faster propulsion systems, more agile spacecraft, and international collaboration. Each interstellar discovery pushes the horizon of possibility further, inspiring practical innovation in pursuit of understanding. The sheer narrative of scale and motion also adds to the sense of grandeur. To visualize a colossal object larger than the cities of Earth combined, hurtling across millions of kilometers in mere days, is to grasp the immensity of cosmic dynamics. These visitors are not rare in the universe. They are only rare in their detection. Countless interstellar wanderers probably traverse the galaxy at any given moment. We see only those that chance to pass near the sun, illuminated long enough for us to notice. The current object, in its massiveness and its eerie convergence with 3I/Atlas, is a reminder that space is alive with motion and that we are situated in a cosmic crossroads. The colossal interstellar object streaking toward the inner solar system continues to grip scientific and public imagination, because every new observation seems to reveal fresh layers of complexity. Its trajectory is unlike anything normally witnessed among local celestial bodies, and the fact that its path intersects with 3I/Atlas transforms it into one of the most astonishing cosmic dramas of our time. While initial reports emphasized its size and velocity, researchers are now exploring far subtler implications that expand into nearly every realm of astrophysical thought. The situation demands contemplation not only of what the object is, but also of what it represents for our understanding of cosmic processes. One of the most tantalizing aspects concerns the possibility of surface diversity. Early spectral data suggests that this immense body might not be homogeneous. Instead, different regions could display contrasting signatures, some resembling rocky asteroid-like crust, others showing signs of volatile rich ice or even organic compounds. This patchwork nature would imply a tumultuous formation history, where fragments from distinct regions of a protoplanetary disk were welded together. If this interpretation holds true, the object is a literal geological mosaic of a distant star system. Observing such heterogeneity at scale would allow astronomers to construct detailed hypotheses about the environment from which it originated, whether that be a young and chaotic planetary nursery or the shattered remains of a once stable planetary body destroyed by gravitational upheaval. The sheer durability of this body is also remarkable. To survive ejection from its parent system and then endure untold millennia of interstellar exposure, it must possess structural integrity that resists cosmic erosion. Between collisions with high-energy particles, bombardment by micrometeoroids, and relentless exposure to galactic cosmic rays, most smaller fragments would disintegrate or erode. Yet this giant persists, testimony to the resilience of matter forged in stellar crucibles. Its surface, likely weathered into hardened crust, may act as an archive of its voyage. Layers etched by radiation, pitted by impacts, and darkened by cosmic chemistry could reveal timelines of exposure, enabling scientists to reconstruct its journey across light years of space. Each scar on its surface is not random damage, but a chronicle of time beyond the reach of human lifetimes. The approach of this object also forces a re-evaluation of galactic traffic. Traditionally, the notion of interstellar objects visiting the solar system was considered an extreme rarity. Yet within just a few years of modern survey capabilities reaching full power, humanity has recorded several such arrivals. Now with this massive intruder targeting 3I/Atlas, the perception of rarity diminishes. Perhaps the galaxy is filled with far more of these bodies than previously suspected, drifting unnoticed through the darkness. If so, the solar system is not a static bubble, but an open crossroads where the detritus of countless stars occasionally mingles. This realization recalibrates the models of planetary system evolution, because for each ejected object we see, humanity has recorded several such arrivals. Now with this massive intruder targeting 3I/Atlas, the perception of rarity diminishes. Perhaps the galaxy is filled with far more of these bodies than previously suspected, drifting unnoticed through the darkness. If so, the solar system is not a static bubble, but an open crossroads where the detritus of countless stars occasionally mingles. This realization recalibrates the models of planetary system evolution, because for each ejected object we see, millions more remain invisible. The current event highlights the universe's ceaseless movement, where stars and planets are not isolated but participants in a larger, continuous exchange. The question of dynamics invites deeper examination. If this trajectory is not mere coincidence, then forces beyond random chance are shaping interstellar movement. Perhaps large-scale gravitational corridors sculpt the flows of matter across the Milky Way. Imagine streams of debris threading through the galactic spiral arms, akin to rivers guiding logs downstream. In this vision, our solar system is momentarily intersecting one of these invisible channels. If verified, the discovery of galactic highways would revolutionize astrophysics, providing insights into how stars share material, how interstellar chemistry is homogenized, and even how seeds of life might spread from system to system. The interstellar object heading toward 3I/Atlas could thus be more than a physical body. It could be a visible marker of hidden galactic architecture. Cultural reactions to this event also merit exploration. Humanity has always viewed the heavens with a blend of reverence and apprehension. To know that a gargantuan alien body is barreling toward an intersection with another interstellar traveler stirs primal instincts of both fear and awe. Artists, writers, and storytellers may interpret the convergence as a cosmic dance, a duel, or even a rendezvous scripted by forces greater than ourselves. Philosophers may see in it a metaphor for human destiny, the meeting of separate journeys in a single moment of contact. Religious traditions may revive ancient motifs of omens in the sky, reinterpreting them through modern discovery. These reactions matter because science does not exist in a vacuum. It reverberates through culture, shaping how humanity perceives its place in the cosmos. The convergence also challenges instrumentation. Telescopes optimized for tracking near-Earth objects must push their capabilities to capture sufficient detail of a body moving so swiftly and so distantly. Adaptive optics, high frame rate imaging, and distributed arrays are being coordinated in ways rarely seen outside planetary defense drills. Space-based observatories, sensitive to infrared and ultraviolet ranges, provide complementary data that Earth's atmosphere filters out. Together, these technologies stitch a more complete picture, but the task is daunting. Each observation window is narrow, each miscalculation a lost opportunity. The very pursuit of this object accelerates technological innovation, pushing astronomers to refine techniques that will serve future generations of cosmic exploration. Another captivating possibility lies in the interaction zone, where the object's trajectory intersects with 3I/Atlas. If the two bodies pass within a sufficiently close distance, their gravitational fields could subtly influence each other. While they are far too distant from Earth to endanger us directly, even a fractional deflection is significant on astronomical scales. Observing such a nudge between two alien bodies would be a first in human history, offering direct empirical evidence of interstellar gravitational encounters. Models could be validated or overturned, reshaping how scientists simulate the movement of debris across the galaxy. It would also hint at a broader cosmic truth, that these wanderers are not solitary but part of a larger ballet where interactions, however rare, weave a pattern over eons. Speculation naturally extends to the nature of what might be hidden beneath the surface of such a massive traveler. If the object contains significant amounts of frozen volatiles, it may erupt into cometary activity as solar heating penetrates its crust. Outgassing jets could spew plumes of vapor and dust into space, revealing pristine material from its interior. These emissions would provide unparalleled clues about interstellar chemistry, perhaps showcasing compounds rare or absent in our own solar system. The potential detection of complex organics would ignite debates about panspermia, the hypothesis that life's building blocks are distributed across the galaxy by such objects. While no one suggests that this body carries life itself, the presence of prebiotic molecules would demonstrate the universality of chemistry that leads to life. Beyond the realm of science, there is the symbolism of scale. Human civilization often orients itself around events on Earth: wars, discoveries, crises, and triumphs. Yet the universe occasionally reminds us that forces unimaginably larger and older than us remain in motion. A city may seem vast, a nation powerful, But when compared to a celestial body spanning dozens of kilometers and moving at incredible speeds, these constructs shrink into insignificance. The arrival of such a giant challenges human hubris, replacing it with humility. This humility is not despair, but perspective, a reminder that our world is both fragile and extraordinary within a cosmos still filled with mysteries waiting to be revealed. The interstellar giant also touches on the theme of temporality. Light from stars we see tonight may have traveled for centuries to reach our eyes, but this object itself has traveled in physical form across countless epochs. It may have left its birthplace before humanity even evolved, drifting silently through darkness until fate aligned it with our solar system. Its journey is a living chronicle of deep time, one that dwarfs the span of human history. To observe it is to brush against eternity, to glimpse a moving fragment of a story that stretches far beyond human timelines. In this sense, the object is not merely matter but memory, carrying within it the record of cosmic processes long past. The prospect of future missions cannot be overlooked. While current technology makes intercepting this particular object unrealistic, its arrival fuels ambition. Engineers and scientists will look at this event and ask, how can we prepare for the next? Could faster propulsion systems, such as nuclear thermal rockets or solar sails, enable interception of future interstellar wanderers? Might swarms of microprobes be launched to rendezvous with such bodies, transmitting close-up data before they vanish into the void again? This event becomes both a challenge and an invitation, a reminder that interstellar exploration may not always require waiting for distant stars, but can begin with the objects that come to us. There is also the possibility that this visitor will refine our definitions of what interstellar objects are. Perhaps classifications must expand to include categories beyond asteroid-like or comet-like. With its sheer size and peculiar targeting of 3I/Atlas, it may fall into a new class altogether: giant interstellar planetesimals or rogue fragments from planetary collisions. Establishing such categories helps science build conceptual frameworks, but it also stretches language itself. Humanity may need new words to describe phenomena that defy current taxonomies. This linguistic evolution parallels scientific discovery, as every breakthrough enlarges the vocabulary through which we engage with the universe. The encounter further underscores the importance of collaboration. No single observatory, agency, or nation can track and analyze such an event alone. Networks spanning continents and even amateur astronomers with advanced equipment play roles in the effort. This collective endeavor mirrors the object's scale. Something so vast requires humanity to pool its talents. International data sharing, cooperative planning, and distributed observation campaigns embody a kind of unity that mirrors the interconnectedness of the cosmos itself. In chasing this interstellar traveler, humanity also practices cooperation on a global scale. The implications ripple even further into future human exploration of the galaxy. If large interstellar objects are more common than once believed, then the void between stars is not truly empty, but populated with waypoints. These bodies might one day serve as stepping stones for interstellar travel, offering resources such as water ice for fuel and shielding, or simply serving as landmarks along routes. The giant now approaching may be a harbinger of this vision, that humans venturing beyond the solar system will navigate not only to stars, but among the interstellar debris that drifts between them. Thus, the current event is not only about science today, but about the possibilities of tomorrow. At its core, this convergence speaks to curiosity. The universe has delivered an enigma, a giant body on a path intersecting with another alien traveler. No one commanded it to come. No one predicted it until the last moment, yet here it is, offering itself as a mystery to be unraveled. This unpredictability is the essence of exploration. Humanity does not choose the cosmos' surprises. It can only respond, observe, and learn. The interstellar giant reminds us that discovery is not about controlling outcomes, but about encountering the unknown with readiness and wonder. Every passing night of observation builds the story further. Data accumulates, theories proliferate, and imaginations ignite. The object becomes more than itself. It becomes a mirror of our capacity to look outward and question. Its immense bulk, its extreme speed, its alignment with 3I/Atlas. All these elements combine into a single cosmic tableau that captures not just the mind, but the heart. It is a story of the galaxy writing itself across our skies, and for now, humanity is the fortunate witness. The immense interstellar object racing through the void toward the solar system carries with it not only physical intrigue, but also intellectual gravity that bends the focus of entire fields of science. Already it has transformed from a curiosity into a focal point where astrophysics, planetary science, cosmochemistry, and even philosophy converge. The uniqueness of its trajectory toward 3I/Atlas forces questions that stretch far beyond orbital mechanics. It challenges humanity to reframe its understanding of interstellar matter, cosmic coincidence, and the very architecture of the Milky Way. One of the most striking dimensions of this event lies in the challenge it presents to long-established statistical models. For decades, scientists assumed interstellar objects drifting through the solar system would be exceptionally rare, perhaps appearing once every few centuries. Yet within a relatively short span of advanced sky surveys, multiple such bodies have been detected, culminating in this titanic traveler. This contradiction between expectation and reality compels a revision of probability models governing interstellar debris. Perhaps ejection of material from planetary systems is far more common than assumed. Violent gravitational dynamics, especially during early stages of planetary formation, may regularly hurl massive fragments into galactic space. If so, the galaxy is teeming with lost worlds, scattered pieces of creation that roam aimlessly until caught briefly in the light of distant suns. The current object is not an anomaly but part of a vast unseen population. The very origin of such a body sparks a cascade of possibilities. One scenario imagines it as the core fragment of a disrupted exoplanet, ripped apart by tidal forces near a massive gas giant or even a binary star system. Another envisions it as a survivor of catastrophic collisions in a young planetary nursery, where protoplanets smashed into each other and ejected remnants into the interstellar medium. A more exotic theory proposes that such objects could be relics of supernova events, hardened pieces of planetary systems blasted outward when their parent stars exploded. Each hypothesis connects this traveler to cataclysms of scale and violence beyond human comprehension, events so powerful that they shape not only their own systems but the galaxy as a whole. Attention has also turned toward its potential influence on the heliosphere, the bubble of solar wind that surrounds and protects the planets. A body of such mass slicing into this region may produce subtle but measurable effects. Plasma flows, magnetic interactions, and even cosmic ray propagation could shift as the object carves through solar space. If instruments capture these changes, it would be the first direct measurement of how an alien body interacts with our star's protective shield. In this sense, the event provides an unplanned experiment in heliophysics, showing not just the object itself, but how our solar environment responds to intrusions from beyond. The possibilities extend into chemistry at the most fundamental level. If the object begins outgassing under solar heating, the molecules released may include isotopes or elements forged under conditions unlike those found in our neighborhood. Ratios of oxygen, carbon, nitrogen, or noble gases may carry the imprint of a star with different metallicity than the Sun. Such measurements would not merely expand the catalog of known compounds, but offer evidence of stellar diversity written into solid matter. In particular, isotopic anomalies could provide confirmation of processes like nucleosynthesis occurring in environments far from our galactic region. Every puff of gas or dust ejected into space would be a sample couriered across unimaginable distances, decipherable by instruments into stories of alien stars. From another perspective, the object provides a rare chance to examine galactic kinematics. By measuring its velocity and extrapolating backward, astronomers can attempt to trace its path through the galaxy. Though uncertainties abound, even a rough reconstruction could point toward the star system that birthed it. If that parent system can be identified, perhaps a known star within a few hundred light years, then the object becomes a physical link between us and that system. For the first time, we would hold tangible evidence not only of exoplanets existing around distant stars, but of material literally arriving here from them. The idea transforms interstellar exploration from a distant aspiration into a present reality, albeit one limited to fleeting observation. Another dimension emerges when considering its sheer gravitational mass. Even though the object will not come close enough to Earth to exert dangerous pulls, its passage through the solar system may disturb smaller, less stable objects. Certain long-period comets, fragile Trojans, or distant asteroids could experience minuscule perturbations,